Well, greetings everybody. Welcome to video 3 on the series for the Selectron, the SB-256 electrostatic memory tube. In this video, we're going to go through the write process, how I establish two very stable potentials on the storage eyelets, the bits, if you will, how they stay that way, how we change them during the write process. We'll go through a little physics there. Then we'll address the circuit that I use to implement this. We'll correct a small oversight from video 2. And then finally, I'll show you some timing diagrams for the final circuit and sort of wrap this up and show you how I put together this introductory sequence here. We now want to discuss how these eyelets can store by-value information. And we associate that with ones and zeros in today's digital vernacular, but the eyelets are actually going to be at two different potentials. One potential will be near 0 volts. The other potential will be near the collector potential of 180 volts. So how is it that this eyelet, being electrically isolated, can be stable at either 0 volts or 180 volts? So that's what we're going to go through today. And as usual, I'm going to start from the technical report, the RCA review technical report, and we're going to start with a couple of pictures from that report that deals necessarily with the eyelets, how we store potentials, how we store information, how we change that and read and write to these things. So first, I'm going to turn this image around so that it's oriented correctly. And I'm going to point out in this image here, this is a one-of experiment. This is not how the tube is wired in real life. So this is an aside experiment, a one-of experiment, just to document an IV curve. So what we've got going on here is the eyelet's being biased at some potential, and I'm measuring the current on it. Now, I'm going to show you a cartoon of this in a moment, but I also want to draw your attention to the fact that this eyelet is isolated. It is isolated, electrically isolated from the collector and from the write plate. It's like we've got an effective capacitance connecting these three elements together. And that effective capacitance is on the order of 1 picofarad. Now, this curve we get by measuring the current on the eyelet as I ramp up the potential on the eyelet. Now, what I'd like to do is go through this diagram with some cartoon drawings of the cathode and eyelet. So let's have a look at a cartoon drawing of this curve. This is qualitatively similar. It is representative of that curve, and we're going to use it to explain a couple of things. First of all, I want to explain how it is that I can have negative currents or positive currents, or again, negative currents, depending on the potential of the eyelet. So I have three different situations here. The little gray square is the eyelet. And of course, that's the cathode. Now remember, this is a one-of experiment. The eyelet is physically and electrically connected to a voltage source, a power supply. And remember, a voltage source, its job is to provide whatever charges are necessary to maintain the voltage that we've set. So in the situation where I am, say, less than 50 volts, we are collecting electrons from the cathode, this primary electron beam. But since I am, say, less than 50 volts, 25, whatever, I may not be capturing all that's emitted by the cathode. There are certainly electrons going to the collector, since the collector is at 180 volts. So this electron capture or collection, whatever, on the eyelet, this is going to show up as a negative current on this ammeter. Next, we look at this region, say between 50 and 180 volts. And we still have our primary electron beam. I drew it with an extra ray just to sort of represent that we may be capturing more of the total that's being emitted by the cathode. At any rate, we have a positive current here. So how is it I have a positive current registered by this ammeter, even though I have electron flow? The answer is in secondary electron production. And I'm going to spell secondary like that. So To get a positive current registered by my ammeter, I would need to emit or eject more electrons from the bulk than electrons falling on it. So let's draw some more. So I've drawn, let's count these, approximately 2 secondaries for every primary beam that's coming in. That's definitely going to register as a positive current. Where do these secondaries go, you might ask? Well, since I am less than the collector potential, always less than the collector potential, these secondaries will find their way to the collector, hence the name. Finally, we want to consider eyelet potentials greater than 180 volts. In this case, and you notice that my current asymptotically approaches some value, this means that I am collecting probably pretty much 100% of whatever's being emitted by the cathode. We'll draw it like that. And again, this is greater than the collector potential. So this is going to tend to pull in electrons that may have been headed towards the collector otherwise. So I'm asymptotically approaching some value. In secondary electron physics, this would be the infinity, the I naught, the incident current, or whatever. I may still produce secondary electrons, but since the eyelet potential is greater than the collector potential, any secondary that's produced here will eventually find its way back. So we end up with a negative current again. So this simple cartoon diagram should qualitatively explain the nature of this curve. This curve is necessary to explain how the eyelet can be stable at 2 different potentials when it's floating. So we're going to cover that next. So we're going to use this curve again, and we're going to look at it now in the situation that is actually in the tube. We have our collector, our right plate, our eyelet. The eyelet is electrically isolated. It's completely floating. The only connection to the collector and right plate is through the mica that capacitively couples them. This will be important in the right process, but for right now, for static equilibrium purposes, we could ignore that. Now, why do I need a QS and electron beam to maintain an eyelet potential? And what are the stable eyelet potentials from this? So what we're going to do is we're going to start and assume that the eyelet is near 0 volts. So if we're near 0 volts and we have some perturbation to the eyelet, some leakage current, some whatever that might somehow change the potential in this eyelet and make it a bit more positive, the eyelet will find itself a bit more positive like this. But what that's going to do, once I am on this part of the curve, I have negative current falling on the eyelet. And what's that going to do? That's going to tend to lower the potential of the eyelet. So this ends up being a stable potential for the eyelet. And actually, it'll be slightly negative because of the thermal distribution of the electron beam, but we're just going to call it 0 volts and label it V0. Next, let's assume that VE is near this crossing point here. It's in the actual tube, it's about 50 volts here. Let's just call that 60 volts. We are dead on where the current, the net current on the eyelet is 0. But we need to see how stable this potential is to perturbations. That is, if there's some kind of leakage current, some little wiggle that tries to change the potential of the eyelet. First, let's consider a wiggle where the eyelet potential lowers a little bit. Let's say the eyelet potential lowers, and then what happens? Well, we end up with a negative current falling on the eyelet. And what's a negative current going to do on this eyelet, which is completely floating? Well, that's going to lower the potential on that. We're going to keep lowering it, and it's just going to end up going back to V0. This is not stable. On the other hand, let's say we wiggled it a little bit more positive, and VE is a bit higher. What's that going to do? Well, now I have positive current falling on the eyelet. Positive current is now going to tend to raise the potential. So this point, VA, as it's labeled, is unstable. So that is not a stable operating point for the eyelet. Then our next crossing is at near 180 volts, the collector potential. So let's assume it is that. And then let's think through, well, what happens if something wiggles this potential? If something wiggles the potential to be a little bit higher, let's just go that direction. If the potential ends up being a little bit higher, what does that do? I am now on the negative current side of this curve. And with negative current, we will lower the potential. In other words, make it return to here. On the other hand, if something wiggled the eyelet potential and perturbed it, made it a bit smaller, that's going to put us on the positive current side. And of course, that's going to raise our potential. So what we end up with are two stable potentials. So why do I need this maintaining quiescent incident current in the idle state of the tube? Well, the answer is I need this maintaining current to sort of self-correct any small perturbations in the eyelet potential. If something just tries to gently, make this eyelet a smaller potential, say leakage currents, whatever, I would need this incident current just to sort of self-correct that small change. So we're now ready to look at how do we write values? How do I change these potentials? Let's say this represents a digital 1 and this represents a digital 0. How do I write 1s and 0s? How do I change the potential on the eyelet? So now we want to take a look at how I change the potential of the eyelet during the write process. So this is our representative diagram of the eyelet, collector, and write plate as it is in the tube. We have no longer connected the eyelet to anything. We're done with that. It is electrically isolated. The only connection the eyelet has to the outside world, that is the collector and the write plate, is by this capacitance. There's a mica layer that separates all of these. So we effectively have a capacitor here. So we want to look at how do I change the stable potential of the eyelet? Let's say I'm wanting to go from a low to a 1 or a high. That is, the eyelet potential is near 0 volts, V0, and I want to bring it to VC. How do I do that? Well, what we're going to do first and foremost is deselect all other eyelets before I start this process. I deselect all of them so that when I do my right plate pulsing and so forth, nothing happens to the other eyelets. I don't change their values. But I have selected this one eyelet. I've got the window open for just this one. And then what we're going to do is we're going to apply a pulse, a positive pulse to this right plate. So the way I'm going to draw this, I'm going to draw my pulse. This will be a little unorthodox. This axis will be time, and then this axis will be voltage. So what we're going to do is apply a positive pulse to this right plate. I'm going to start from near 0 volts on the right plate, and we're going to bring it. I'll tell you the value in a moment. We need to go from at least 50 to 180 volts with our eyelet if I'm going from a 0 to a 1. So what is that? 180 minus 50, 130. And given the capacitance here and the rest of the circuit, we need to double that. We need at least 260 volts here. But the technical report, the patent information actually recommends a safer, or something that's going to absolutely make sure that this happens, 360 volts on this right pulse. So we're going to put 360 volts on this right pulse. Now, what does that do to the potential of the eyelet? Remember, they're capacitively coupled, and this very sharp turn on through displacement current will raise this potential of the eyelet. It's going to happen fast enough that this maintaining current will not be able to change anything. So we're going from near 0 volts. I'm just going to draw offset just a little bit in time. So we're going to bring it a half 360 if I'm starting at 0. Again, we've got this capacitance also to the collector at 180 volts. We're going to raise it up to some value greater than 180 volts, and we're going to stop there for just a moment. Now, we need to leave this right pulse on at 360 volts for just a little bit. Why? Well, we want the potential of the eyelet to decay or be maintained back to the stable potential of 180 volts. So we're going to let this in time, we're going to let this come down to our 180 volts. So I need to let my right pulse be on for at least that amount of time. Then what do we do? Remember, I went from a 0, now we're at a 180 volts. I need to return this right plate voltage back to 0. But if I bring it down abruptly, I'm going to have the same thing. I'm going to have the displacement current. It'll bring it instantly down to 0, and my maintaining current will not be able to do anything. So what we do is we bring it down slower, such that, yeah, we're going to start bringing down the collector potential. But since I'm now in this positive current region of this curve, the maintaining current will tend to try to push it back up. So as the right plate potential ends up all the way back down to 0, we may see our eyelet potential do something like this. And I'll show you some simulations in a minute with Spice, but this is the idea. When I'm writing a 1, I'm going from a 0 to a 1. I bring up my right voltage and my right plate to 360 volts as fast as I can. I leave it there so that once, if I've overshot this 180 volts, the eyelet potential will come back down. Then I slowly lower the right potential so that this maintaining current has a chance to bring this back to 180 volts. Now, what if I want to do the opposite, 1 to a 0? Let's do that. Now we want to go from a 1 to a 0. The process is similar. We're starting here, and I want to end up here. We're going to use the exact same right pulse. So we have our right pulse doing that. And we're starting at a 1 or 180 volts. V eyelet is 180. And we want to go to 0 volts. So if I start at 180 volts here, this sharp turn on is going to bring the eyelet potential very positive. But we're going to leave this on for a while so that the eyelet potential has a chance to self-correct and come back to the 180 volts. So it'll come back down eventually. We want this to happen before we turn off the right pulse. That will give us a decay that looks sort of like that. Then, now what? We want 0 volts, and we're going to bring this down slowly. What we have to do is turn off this incident current so that this incident current does not have a chance to sort of self-correct this potential. So what happens is this guy will sort of follow a curve going down, because the only current going to the eyelet is the displacement current through this capacitive coupling. We don't have this incident quiescent current. So in the case of writing zeros, I have to deselect this incident current. So what about eyelets that were not selected during this process? Does their potential change when I pulse this right plate? Remember, they're connected. This right plate is connected to every eyelet on there. So unselected eyelets. Unselected eyelets will not have this quiescent incident electron current on it. So if my unselected eyelet starts at VC or at V0, when I apply my right pulse goes positive 360. That will raise the potential of the eyelet, but there's no maintaining current. There's no anything going to it. So yeah, it raises the potential of the eyelet, but when I drop the right plate down again, it brings the potentials back. So essentially what's happened is this eyelet has kind of gone for a potential ride, if you will. It will come back to the original potential as long as I've turned off this quiescent electron beam. So I wanted to summarize with this one eyelet again, sort of the timing diagram for writing information to these eyelets. Remember, we start with the tube in the idle state. That is to say, we have all windows open. We have electron current falling on all eyelets, which is being used, again, to sort of maintain these two stable potentials. Then, if I want to write to a particular eyelet, what I need to do is deselect all eyelets except for the one I'm interested in. So that's what we're trying to show here. This part, before I start, that is the quiescent state. And then here, I am deselecting all bars except for the one that I want. And then I'm going to come down here. The one that I've selected will stay at 0 volts. And we have our right pulse. At this time right here, just maybe a little safety time after I've deselected, I ramp up the right plate to 360 volts as fast as I can. That will bring the potential of the eyelet. It doesn't matter where it is, whether it's at 0 or at 180 volts. That will tend to bring up the potential of the eyelet. And then we've got to stay at this potential for a little bit. Why? Because I need the eyelet to come back down to this potential at 180 volts before I do any other changes. It will come down naturally to here as long as I have my selected window open and I have this incident electron beam. Now, at this point, I want to turn off the right plate, the pulse, and we're going to bring it down slowly. If I'm writing a 1, I don't do anything to the selected window. It stays open. So if I'm writing a 1 and I slowly bring down the right plate potential, I'm going to bring my eyelet potential down into this region, but as long as I have this maintaining positive current now, I will end up at 180 volts at the end of the day, at the end of the right decay here. On the other hand, if I'm trying to write a 0 during this process here, I have to turn off this window. I need to turn off this maintaining current so that I'm starting here and I'm trying to lower the potential with a right plate pulse. If I don't turn off this incident maintaining current, it will try to keep the potential, because we're going through a positive current region, it will try to bring the potential up to here. But if I turn off that current, this is not here anymore, and the displacement current through that capacitor will bring the eyelet potential near 0 volts. Now, once I've reached the end of this process, I need to turn on all bars, again, for my idle state, quiescent state, just for the maintaining current. So we've been kind of waving our hands and arguing what happens to the eyelet potential as I apply my right pulse. I'd like to kind of go through this again using a circuit simulator and kind of show you something a bit more precise. So what I'm going to do is start by modeling my eyelet, my incident quiescent current in LT-Spice, and what I'm using is a BI, arbitrary behavior current source, for this, and this is part of the function, but I'm just going to show you that this function that I've got plugged into this thing actually generates an IV curve that's qualitatively similar to what was published in the technical report. So we'll use this function to simulate what happens when I write a 1 or a 0 or what have you. So here we have our circuit for modeling the eyelet. We have the collector at 180 volts. I have this effective capacitance between the collector and the eyelet, approximately 1 picofarad, and then again another one to the right plate, And I'm pulsing the right plate as we do this, and again, I have my arbitrary function eyelet current going in here. But in green, we have the collector potential. It's always 180 volts. I started with an initial condition on the eyelet. It's at 180 volts, and I'm going to write a 1, which is still no change. But what happens when I apply my right pulse, the eyelet potential goes up high, but then this maintaining current will bring it back down. And then if I bring down my right pulse slowly, I bring the eyelet potential to this region where it's effectively a positive current, and it doesn't go down much further. Now, what if I started with the eyelet at 0 volts? And let's just run this again. So I have applied a right pulse that's going sharply up to 360 volts. That brings the eyelet potential up to near 180. And then I slowly lower the right potential. And again, I do this slow enough so that the maintaining current will keep this near 180 volts. And after the process is over, I have effectively gone from a 0 to a 1. So then, what do we do if I want to write a 0? So here we're trying to write a 0, and I'm going to start with the eyelet initially at 180 volts. That would be a high. And let's just run this real quick. The eyelet starts at 180 volts. It's now red. And I apply my right pulse. That's going to bring the eyelet to a very high potential, but it does eventually come back down. That's why we need this plateau to stay on for a bit. But when I start bringing down my right potential, I need to turn off the current, this maintaining current that's going to the eyelet, so that whenever I bring down my right plate potential, the eyelet potential will come down with it. So I've effectively gone from a high, 180 volts, to a low, near 0 volts. Now, what happens to an eyelet that was not selected during this process? Let's look at that. So here I have a file that I've named eyelet unselected, but I haven't deleted anything yet, and this is the simulation for it. But what I'm going to do is turn off or just take away this current source that will effectively remove this incident current. And then we're just going to run this again. And we see, let's see, we've got the V of the right plate. It's going up 360 and then back down again. My eyelet started at 180. It just went up with the right pulse, and then it comes back down. It just went for a potential ride. And if I start with my eyelet at 0 volts instead, we'll get a similar result. The eyelet in blue just went for a potential ride. That's all it did. So unselected eyelets during the write process, yes, there are potential changes, but since I don't have a maintaining current on it, their potential at the end of the day never changes after I'm done with the write process. So let's have a look at the right plate driver, the electronics I'm using to drive my 0 to 360 volts controlled with TTL. The design is very similar of that of the selector bar driver, and this is probably a good time as any to mention an oversight that was presented in video 2. You may recall I attributed the slow turn-on time of the selector bar voltage to stray capacitance of the selector bar and stray capacitance of the wires. Who knows, I may have even blamed the phase of the moon, but I completely forgot about the input capacitance of these MOSFETs. That's going to have a significant bearing on the turn-on times here. So returning back to the right plate drivers, I am simulating MOSFETs that are in the package. Actual MOSFETs that I'm using in circuit are highlighted here with the little arrows. Unfortunately, these MOSFETs aren't in my SPICE package to use as a model. We see that the MOSFETs that are being used in the model have a higher input capacitance than what I'm using out in the circuit. So that'll give us a really good idea of what's going on here. So on the input, I have my digital in here, 0 to 5 volts, turning things on. And you kind of see these two gate voltages. Gate 2 is this guy. Gate 1 is the one going over to the P channel, so they kind of look like this. And you can kind of see the slow turn on and turn offs here. And then, of course, the right plate is this guy on the top. And it does go from 0 to 360, kind of like I want. We do have this tail that could be attributed to the slow turn off of these gates. It could also be due to the very real right plate parasitic capacitance. This is 200 picofarads as stated in the technical manual or the technical report, I should say, and the patent information. And actually, this slow turn-off is very fortuitous. I don't have to control my right plate potential coming back down. This is slow enough of a decay that we can still write ones and zeros. So let's go see how this works out in the lab and look at actual timing of the real circuit. So we're out in the lab. We're going to have a look at all the signals necessary to generate that introductory sequence. I have 3 of my oscilloscope probes on the TTL digital control signals for select, write, and the quiescent point. I also have 1 more probe on the high voltage of the right plate. So then let's have a look at what's going on the oscilloscope. And we see here channel 1 is the right, channel 2 is the select, channel 3 is the Q point, those are the TTL signals, and then finally channel 4 is the high voltage that's actually going to the right plate. And you may notice that it toggles between sort of a long pulse and a wide and a short pulse. This is when we're either writing ones or zeros, depending. So let's have a look at this timing diagram in a little bit greater detail. So here we have a screenshot taken from the oscilloscope. This is representative of when I'm trying to write a 0 to the storage bit. The process starts by first addressing the bit that I want, that is, deselect everything else. So we set the address and we raise the quiescent point line up to a 1. This basically deselects everything except for the bit that I want. Then I raise the right plate potential to 360 volts, so this right pulse goes high. And we have to wait a certain amount of time for the eyelet potential to come back down to 180 volts if it were high. Now if I'm trying to write a 0, what I need to do is then deselect that 1 bit. That turns off the current to the eyelet. And then when I bring this right plate down to 0 volts and it just sort of decays down, we don't have this maintaining current, and that will bring the eyelet potential down. Now, I wait a little bit of time for this to happen before I turn on the select again. That reestablishes the potential for the 1 bit, and then I wait just a little bit longer, and then I reestablish the quiescent point so that all eyelets have their maintaining current again, and then the process has ended at this point. We could shorten some of the time on this, but I'm not trying to make a super fast machine here. After all, we're not going to try to compete with a modern flash drive or anything. Just demonstrate operation. Here is our timing diagram for when I'm writing a 1 or a high to the eyelet, and it's significantly shorter because I don't have to deselect the bit and wait for things to stabilize at that point. I can just bring the right plate down from 360 to 0 while leaving this maintaining current on. Now, you may notice that there is a time delay from the actual TTL signal and then the actual high voltage that reaches the plate. This is entirely due to the input capacitance of those MOSFETs. The decay of the right pulse from 360 to 0, that's also determined by the parasitic capacitance of the right plate. The 1 bit that may not be working in the introductory sequence, this could be because this right decay is too fast. If it's too fast, I won't be able to establish a 1. That would be sort of the symptom of this. So I may go in and intentionally add a small capacitance and see if that helps. But other than that, that sort of wraps up this video. This is sort of an instruction on how we do the right process on this tube. So thanks for playing along.